All right, we can keep going here. I wanted to talk about RC circuits today. Before we get into RC circuits, this is going to be very similar to what we did for the resistor and inductor circuits. I want to go through the RC part with a slightly different notation than we did before, because it'll make it a little bit some shortcuts in the math, I guess. And basically, that's using the phasor notation. So we're going to use this because we decided that we could write by converting our resistances and reactances to impedances. We can add everything together just like the regular rules for adding resistors in series and parallel. So we're thinking about this number, this variable v being a complex number, so it's got a real component and a complex component. So the real and the imaginary part. And you can kind of treat these complex numbers like vector, where it's so much in along the real axis and then so much on the complex axis. So this is going to look a lot like doing vectors. So in that kind of idea, you can write this another form as magnitude times cosine of phi, the real part, the magnitude times the sine of phi for the imaginary part, and j, remember that is our square root of -1. So this is kind of like switching between rectangular and four coordinates. So how we can think about writing this quantity v in this phasor notation. One second. We're going to write that as magnitude of v. Take into account the angle. We're going to use this symbolic notation, angle phi. If you want to figure out what this phase angle of phi is, it's the inverse tangent of the real component over the imaginary component over the real. So inverse tangent of vi over vr gives you that phase angle. The main reason that I want to do it this way is because like I mentioned before, if I have two of these complex numbers, a that I write as its magnitude times phase angle same thing for another quantity b. I want to start doing stuff like multiplying a and b together, or like what we'll do today, dividing a and b. polar or phasor notation works really good for the multiplication and division. So you divide their magnitudes. And you subtract their phasor phase. So here's where I'm going to make a little bit of a distinction. This behaving a lot like we're doing vectors. This is, and that's really what's going on with the putting in these complex numbers. It's working similar to being at a vector. This division here that I'm talking about, this is not vector division. This is dividing two complex numbers. Same thing if I wanted to multiply A and B together. Multiplying complex number in A times B, I would multiply their amplitudes. And then I would add their phases together. This multiplication here is multiplying two complex numbers. It's not vector multiplication. This isn't a dot product or a cross product. Not multiplying vectors. I'm multiplying together two complex numbers. The complex numbers kind of behave like this. Okay. Questions on that? Okay. So the first circuit I want to think about today is a resistor and a capacitor in series with an AC voltage source. And for right now, I'm interested in the voltage across the capacitor. So I'm going to see if I can figure out some way of expressing this output voltage here. Let's say this AC voltage that we start with, we'll just call that V. So ultimately, what we're going to be looking for is the ratio of the output voltage to the input voltage. So we're going to look at the voltage gain on the capacitor. So when we did this for the inductor, we kind of started off by doing KVL and writing V, IR, L, DI, and we kind of essentially just solve that differential. Here, since we already know a little bit, some more advanced techniques, we don't have to do it that long. Both the resistor and the capacitor have an impedance. And I know that two things in series all I have to do is add up their impedances. The impedance with a resistor, that's easy. It's just its resistance. Capacitor, we add into that. So its impedance was complex, and it's J times reactance. And eventually we're going to get rid of reactance. But for now, remember that the reactance was 1 over omega c. So really what we're going to do is apply Ohm's law to this equation, to this circuit. Because we've got it down to one thing. We combine together the resistor and the capacitor as a single thing with a complex impedance. When I talk about things in terms of impedances, I can use regular Ohm's law. So in this simple circuit, Ohm's law just looks like that. The input voltage is our current times the total impedance. V equals IR is what we usually did. Now we're doing V equals IC. So we kind of need to, so I'm going to switch over to working in phasor notation. So really what we're kind of looking at here is looking at this as a complex number. Got some resistance going in the, so the resistance term is just a real number, so it's along the real axis. The capacitor is 90 degrees out of phase. The capacitance is always going to be down on this polar graph. And its reactance is what we're going to use instead of its resistance, instead of a resistance. Just graphically in that picture, you can figure out what this total impedance is. It's going to be the square root of R squared plus XC squared. It's a complex number. So we're going to write this in phasor notation. So that's the magnitude. It's really just the length of the hypotenuse. That's all we're doing. The angle that I need here, I'm going to write that as that's kind of the messy part. The angle is the inverse tangent of XC over R. So if you're okay with a little bit of simplification, let's just call that the relative phase. So our phi that's in this phasor notation, that's inverse tangent of the reactance over the resistance. So I'm basically trying to fill in this Ohm's law equation. I've got the total impedance. The last thing that we can do I'm going to assume that our input voltage starts off with 0 degree phase. It's like our reference voltage. So this Vn, if I look at this in phasor notation, the angle that it's going to have is just going to be 0 degrees. But we need to bring that up, carry that with us for the next part. But I can put this equation and this equation together. So basically what I want to do is current is the input voltage over the total impedance. Put this in phasor notation. So Vn at 0 degrees. And in the denominator, we just have that same expression for the total impedance. So this is our total current that's going through the equivalent impedance C total. So we've got about half of our job done. I want to look at the output voltage on the capacitor. So in order to do that, I'm just going to look at Ohm's law for this capacitor. And basically all that it's doing is V out is going to be the current that we just found. This is a current going through the whole circuit. So that current times the impedance of capacitor. So we're analyzing this circuit as a very simple two things in series. First thing was we found the equivalent impedance. From the equivalent impedance, we found the total current. And now we're going to go back and look at each thing individually. It's a simple Ohm's law analysis. What's complicating it is that we're throwing in impedances instead of resistors. Okay. So we have almost all of this now. Putting together the total current. Is Vn at 0 degrees. Yeah, r squared plus c squared square root. And that's at a phase angle of phi. That's in the denominator. So all of that is I. Now we need to put in the impedance of the capacitor. So that's going to be reactance, so XC. Now we have to figure out how to take into account the fact that this impedance here is purely capacitive, so it's 100% imaginary. That means it's completely along the vertical complex axis. So that phase angle is negative 90 degrees. What's interesting, so what we can do here is start to combine things. I can divide out the V in, and then that's so divide both sides by V in, that gets rid of that, and that'll give me V out over V in, which is what we were looking for. Remember, our whole point of this what does V out over V in look like? And we're really, really close to that. So V out over V in. X C here. That's 1 over omega C. In the denominator, you got this whole magnitude of the total impedance. R squared plus XC squared. Then that total angle is minus phi minus 9. Phi is negative because it's in the denominator, so that comes up as a negative, and 90 is already negative. When we're looking at just the gain of this circuit, just seeing what's happening to the voltage across the capacitor, we really don't need to focus on the phase information. What's more interesting is to just look at the overall magnitude. So forget about the phase for now. Just look at the overall magnitude. So I'm going to do just a quick little bit of algebra. Multiply both sides by the top and bottom by C. And it's going to make our gain look like 1 over 1 plus r squared. 1 over square root of 1 plus r squared omega squared c squared. That's the overall gain on the capacitor. Okay, so let's look at two limits. First, let's make r squared omega c, r squared omega squared c squared a small number. So I want that to be smaller than 1. So r omega c. I want that to be a lot smaller than 1. So take the square root of both sides. And what that tells me is that omega has to be much smaller than 1 over RC. Remember, when we talked about this RC circuit, the product of resistance and capacitance, that tells us information about how long it took the capacitor to charge. It's kind of like the characteristic time of the capacitor. So looking at 1 over that time, it's kind of like looking at the characteristic frequency of the capacitor, like how fast it can discharge and charge. When we're looking at very, so that's 1 over RC is kind of like, so we're comparing our frequency omega to this frequency of the circuit when we're much less than this circuit frequency. The out over Vn goes to 1. So then look at the other limit, very high frequencies. If you did high frequencies, what we're talking about is having r squared omega squared c squared much bigger. So that means that our frequency omega is much bigger than the natural frequency of the circuit. When you're at these high frequencies, this is a big number here. So we're looking at 1 over, a very large number. That's going to be it's going to be a small number overall. For high frequencies, that ratio is going to get small. So what we built was something that lets low frequencies go through, blocks out high frequencies. This is a low pass filter. Just like how we built or talked about a low pass filter for the RL circuit, this does the same thing. It just does it with a capacitor instead of an inductor. Sometimes a capacitive RC filter is better than an inductive RC filter. It kind of depends on the rest of the circuit that's being built around. So for this low pass filter, if I were to give you a plot of what that looks like, this is gonna, in order to make the plot look nice, I'm gonna have to plot the plot it on a little bit of a different graph. Horizontal axis is the log of the frequency. Vertical axis is the log of the gain. And what you would see is this gain would start off flat, roll over, and start to go down like that. This point here, where it starts to roll over, that's a cutoff frequency. So once you get past the cutoff frequency, you start to really attenuate the voltage on the capacitor. So being able to characterize what that cutoff frequency is would be really useful. And what we kind of look at is if you were to think about extending this line definitely, and looking at about where the horizontal line and this line will intersect. That's where it's going to start curving. So we're still going to be able to get that the numerical value. So I wanted to think about not the ratio of the input voltage to the output voltage. I want to think about the ratio of input power to output power. So the two powers that I want to look at the ratio between, it's the power at half the maximum, half max power over the total power. This is going to look like Pmax over Q over Pmax, right? Nothing too complicated. But I was looking at this graph in terms of logarithms. So I want to look at the log of this power ratio. So one thing I can see right away is that the logarithm of two different intensities, that should remind me of it has to do with decibel measuring system where you're looking at ratios of intensities. So I want to look at this as ten times the log of Pmax over 2 divided by Pmax. This is looking at the power ratio in units of decibels. This is something that we can start calculating. It's not hard. Pmax divided by Pmax, that cancels out. So this is ten times the log of half and that, if you just get a number for that, that's at -3 decibels. So that's how we characterize when this curve starts to go off. Is that this cutoff frequency is usually taking the occur at the -3 decibel point. Sometimes this is called the 3 decibel breakpoint. A change in 3 decibels corresponds to a change in intensity factor of a half. In a lot of systems, going to half power is where that's really where this starts to roll over on a log graph. So if you see this 3 decibel in literature or something, it's 3 decibels because that corresponds to dropping the intensity by a factor of a half. You see the decibels a lot more in audio things. That's related to how our ears also perceive sounds. That's a somewhat logarithmic scale also. Okay, so last thing we'll do real quick is just like we did for RL circuits, we did a low pass filter. There's a high pass filter. Same thing for an RC circuit. Now I want to look at the output voltage on the resistor. So a few things haven't changed from what we did before. So we had our input current or our total current I. That doesn't change. We're just looking at the voltage on the resistor now. So all that work that we did before, we just pick that up here. The voltage on the resistor is the current times the impedance of the resistor. This is exactly the same stuff we did when it was the voltage on the capacitor. It's easier now because the complex impedance of the resistor, the Z sub R, that's just the resistance. So we just multiply that by R. So just looking at the magnitude, it's R divided by R squared plus 1 over omega C whole thing squared. So I ignored the phases. If you want those on there, that would be. Zero minus phi. The resistor, you want to do its complex impedance. It's R and the angle is 0. But what we have here is almost the complete opposite that we had for the low pass filter. it looks like 1 over 1 plus this. So in the denominator, it's a square root of 1 plus 1 over omega CR whole squared. And this should work exactly the opposite that the low pass filter did. When we go to high frequencies, omega is big, 1 over something big, small, so it's 0. High frequencies have unity, the output is about 1. High frequencies are not big. For low frequencies, so omega is really, really small. This is a large number. 1 over a large number is small. So low frequencies get blocked out. Just switching over the other component, capacitor to the resistor, we went from a low pass filter to a high pass filter. Essentially, what we did here was a frequency dependent voltage divider. Real quick, voltage divider. Voltage divider look like that. What we built is that. That's also a voltage divider. It also divides voltage based on frequency. Okay, questions? Right, so we built high and low pass filters. The next thing that we're going to talk about on Friday is an RLC circuit. So all 3 things together in one circuit. And from that, we can start to make notch filters and band pass filters. So one more day on AC stuff, and then probably next week we'll get into transistors. Questions? Right, I'll see you guys tomorrow.
See you tomorrow.